Hello again, Physics 30s. In today's lesson, I'm going to review two fundamental wave properties, those being diffraction and interference. And when I say fundamental, I mean it's a property that only a wave could exhibit. And then afterwards, we're going to start to look into the nature of light. So far in this unit of study, we have just been observing how light behaves in certain situations. Like, for example, when light hits a mirror or passes through a lens, what does it do? But we haven't really examined what is light. What is the nature of light? And we're going to start to look into that today. And that's actually going to finish the unit of study off. And it's also going to lead us into the next unit of study on modern physics. Learning outcome is to describe qualitatively diffraction and interference. And let's start off with diffraction. Diffraction is the apparent bending or spreading of waves around corners, obstacles, or through openings. Let's look at this picture. In this diagram, these bold horizontal lines, which I'll color with red, this represents some kind of a wall. And there's a tiny opening in the center of the wall. What I'm doing is, you can imagine this scenario like you're looking at a body of water from like a bird's eye view perspective. And what you can see from the bird's eye view perspective are these horizontal lines that are called wave fronts. On a wavefront diagram, a wavefront just represents the crest of the wave, and the crest would be the uppermost portion of the wave. So what I have happening is this wavefront is starting to approach this little tiny opening. When a wave passes through a tiny opening, it undergoes diffraction. And when it diffracts, it starts to spread apart, or it starts to bend, or it starts to curve, whatever word you want to use to describe that. So instead of the wavefront being a horizontal line, now it's now going to be a curved line. Similar thing would happen if you had a wavefront that approaches instead of going through an opening, this time we approach like a corner or a sharp edge. And again, I can see as the wavefront approaches that sharp edge, part of it starts to, again, curve or bend. You may be wondering, well, how do you know how to draw the way in which it curves or bends or spreads out? This is actually a really, really difficult thing to do. To predict how the wavefront spreads, we need to apply something called Huygens' principle. And I believe that's named after Christian Huygens, we've already discussed before with his contribution to the speed of light and doing that experiment where he was observing when Io first pops up behind Jupiter. Here's what Huygens' principle states. And again, this is what we use to help us predict the way in which a wavefront is going to diffract. Every point on a wavefront may be considered to behave as a point for new spherical waves. This is a really confusing statement. Okay, I'll do my best to explain this. But it's really difficult to explain how Huygens' principle works. Okay, so what I'm going to do is, on my wavefront at the very top, I'm going to draw a bunch of points, a bunch of evenly spaced points on this wavefront. I'm just going to draw 5 of them. What Huygens' principle tells you is that on a wavefront, if you draw a bunch of point sources, now I've drawn 5 here, you could draw as many as you want, or you could draw fewer, although I think drawing fewer might not be good enough to explain how you get the next wavefront. But what Huygens' principle tells you is that each one of these point sources is the source of a spherical or a circular wave. So think of it like this. If you took a pebble and you dropped it directly on top of the point source, what you would get is this circular rippling effect. So you get, perhaps for this point source, you get a little ripple that looks like this. And then for this point source, each point source being the source of a circular wave, you get this spherical wave. This point source, you'd get another circular wave or spherical wave, if you think it in 3 dimensions. Okay, let's go through this as quickly as we can. We'll get this. We'll do one more. So every point source is the source of a new spherical or circular wave. Now, we can use this diagram to predict what the next wavefront is going to look like. One way you might want to think of this is perhaps the next wavefront I could draw just by following like the bottom contour of the spherical waves. And what I mean is this: if I follow the bottom contour, I could just like shade in, just kind of outline the bottom of the circle. So I'm just following the bottom contour of the wave. Following the bottom, following the bottom. Okay, now, obviously this is not what the next wavefront looks like. The next wavefront is a horizontal line, so there seems to be something that's missing. There are a few spots where these spherical wavefronts overlap, so I'll kind of like highlight the areas where they do overlap. When waves overlap, this deals with the other fundamental wave property called interference we'll get into in a moment. But basically, the way it works is if I take one of these overlap areas, so if I take like this one up here, I can kind of transfer that overlap into this bottom area. And I can take this one and I can transfer it into this bottom area. I can take this one and transfer it into that bottom area. So the overlap kind of fills in the gap for me. And then I can now trace the bottom contour, which would now just be, if I just follow it along, now it would be a horizontal line. Okay, now let's look what happens when you get towards you get very close to the wall. So let's say, for example, I had a wavefront that was right here. I'll draw just a few point sources on it. So let's do one right here. Let's do one right here. Let's do one right there. One right here. One right here. Okay, so let's draw the spherical waves from these. So if I draw this one, perhaps it would look like this right here. Problem is it hits the wall. When this wave hits the wall, a wave's just a carrier of energy. So some of that energy is just going to get transmitted into the wall. Some of them might get reflected. Same with this one. You're going to have some of it just get absorbed by the wall or some of it get reflected. Same with this guy. If we draw my spherical wave from that point source, some of that energy gets absorbed, some of it gets reflected. So not a whole lot happens with these point sources because so much of the wave energy is either getting reflected or absorbed by the wall. What I want to look at is this one that's actually facing the opening. So if I draw this one that's facing the opening, that bottom contour of the wave can actually get through. So if I follow Trace's bottom contour, I actually have this curved part here. And then if I just keep propagating that curved part out, I would get these other spherical or semicircular wave fronts that you are seeing. So that's how you apply Huygens principle to predict how you get these different wave fronts. Again, it's not very easy to do. I mean, I try to do my best to explain it, but really we don't need to worry too much about how to predict what these diagrams look like. We're more just interested in the fact in knowing that when a wave passes through a tiny opening or around edges, it starts to spread apart. So that's the important thing we need to be concerned with. Okay, so that's diffraction. The second fundamental wave property we're going to discuss is interference. Interference is what happens when two waves pass through each other. When two waves pass through each other, or they meet, they superimpose. When I say superimpose, they add together. Specifically, what you do is you add their amplitudes together. And what this can do is when they meet and superimpose, you can either get a larger amplitude wave or you can get a smaller amplitude wave. And it's all about how they actually meet with one another. In this diagram, I've just shown two waves. I have one wave that I've drawn in red, and I have one wave that is drawn in green. And if these two meet in some fashion, they can either produce a larger wave, their combined wave, or they can produce a combined smaller one. So let's look at the two different kinds of interference, starting with constructive interference. Constructive interference occurs when waves meet in phase. When I say that waves meet in phase, what that means is that, let's say we drew a vertical line through these waves here. Waves that meet in phase would have the crest of one wave meet the crest of another. Or if you look at the dips here, waves that are in phase would have the trough of one wave meet the trough of the other. When this happens, these two waves will give you a jumbo wave. So for example, let's say we had like a little tiny wave like this, and then I'm going to overlap it with a different color. With this red one. And if we drew these superimposed waves, you just add all your amplitudes together. So basically, crest plus crest would give you twice the crest. So you get like a really big crest. And then trough plus trough would give you a really big trough. So I'd probably expect to see something along the lines of this wave here. So the purple wave would be the superimposed wave. So what's happened is I took these two waves and they met together, and the superposition resulted in a larger amplitude wave. This illustration, it's showing S1 and S2 represent the sources of two waves. This could be like, for example, you just like dropping a pebble into the water and seeing how like the energy radiates outward. We're just going to focus on one wave, the propagation of one wave from these sources. Although, like technically, if you drop the pedal in the water, you'd be radiating energy in every single direction. What I'm interested in is where these two waves meet up. So that's at point P. If you look at point P, what's happening to the two waves at this location? Well, the tops are meeting and the bottoms are meeting. So that would mean at point P, that would be a point where you have constructive interference between the two different waves. If you have constructive interference between two waves, you produce what we call antinodes or maxima. Maxima should not be surprising because what you're doing is you're maximizing the wave amplitude. As for the word antinode, the way I would memorize this, I mean, I don't possess a whole lot of memorization techniques. In fact, I hate memorizing things, which is why I hate biology. But the one memorization technique I have is alliteration. So what I would think here is antinode and amplification both start with the same letter A. Therefore, an antinode is produced when you have constructive interference that gives you a larger amplitude wave. Here's where it gets a bit funky. So now we're going to describe the condition necessary, another condition necessary to get constructive interference. Let's get rid of all this writing. Constructive interference occurs when the path difference between the two waves is 0 or a whole number multiple of wavelengths. That's a very, very wordy statement. I'm going to translate it into a mathematical equation. In this equation, I have one variable that is PS1. PS1 would just represent the distance from P to S1. PS2 would represent the distance from point P to S2. The path difference would be just the difference between these two values. It's telling you how much longer one path is than another one. This is my path difference. We put the absolute value sign around it just to make sure that we do get a positive path difference. Okay, now I'm just going to show you how this works in terms of wavelength. So if we broke down the distance PS1 in terms of the number of wavelengths you see, well, let's count them. Okay, so let's start at S1. We'd have one wavelength, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So PS1, if we actually plug this in, would be 12 full wavelengths. S2, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I'm going to go 12 wavelengths minus 13 wavelengths, take the absolute value of that, and that would just be equal to one whole wavelength. So if you take the path difference between like the source of the wave and a point that you're interested in knowing what kind of interference is occurring at that point, as long as that path difference is either 0 or a whole number multiple of the wavelength, then you do have constructive interference. Now you might be wondering, well, why is that the case? So like, why is it that when it's a whole number multiple of wavelengths, the path difference, you do get constructive interference? Okay, I'm going to try to use my little waves I drew on the right-hand side of the page to explain this. Okay, so I'm just going to end the show so I can manipulate the actual shapes. Okay, so I'm going to take this top wavelength. I'm just going to put it over top of the bottom one here. What I'm going to do is I want to, let's go back to the slide actually. What I'm going to do is I'm going to take one of these waves and I'm going to move it. So from this starting position here, I'm going to take the wave and I'm going to move it over by a whole number multiple of wavelengths. I'll just move it over by a single wavelength. The easiest way to think of a single wavelength would be to go from crest to crest. So I'm going to move this over by one wavelength and see what happens. Okay, let's keep these. Okay, so the wave I'm going to move is the red one. So what I want to do is I want to move the red wavelength over by just one wavelength. Okay, so let's do this very slowly. Okay, move it over that distance of one wavelength. Let's see what happens when it finally gets over by a wavelength. Well, guess what? It perfectly overlaps again. So you've got constructive interference. If you went over by two wavelengths, so I go over by another one here, it's moving over by two whole wavelengths. So if I move it over by a whole number multiple of wavelengths, then I basically just have the wave still meeting in phase. And that's my condition for constructive interference. So that's why, as long as we have a path difference that's a whole number, then we can, whole number or 0, multiple of the wavelengths, then we can get constructive interference. Okay, let's go to destructive interference. Destructive interference occurs when waves meet out of phase, and this results in the wave amplitude being decreased. So in this illustration, when I say waves meet out of phase would mean that the crest of one wave lines up with the trough of another one. If this were the case, like for example, we took one wave like this, and I took a second one, another wave that's completely out of phase, like that. And if you added all the amplitudes together, you would actually just get nothing. So for a brief moment, the waves actually completely cancel each other out. That would be perfect destructive interference. A perfect destructive interference would actually completely eliminate the wave. But if the wave amplitude just decreased a little bit, like say, for example, some waves interacted and like the wavelength or the amplitude is just smaller, that would still be destructive interference. It'd just be like partial destructive interference if the amplitude got smaller. Just like I'd say perfect constructive interference would be like you're doubling your amplitudes, as where like a partial constructive interference would just result in some kind of increase of your wave amplitude. So going back to this picture again, where I have these two sources of my waves interacting at point P. This illustration is probably not as clear as the other one, but if you look at the point P, it's supposed to be showing that the top of one wave meets the bottom of the other, and these waves are meeting out of phase, resulting in destructive interference. This produces nodes or minima. Minima shouldn't be surprising in terms of the term, because what are you doing in destructive interference? You're minimizing the wave amplitude. In terms of memorizing node, I would again use my alliteration technique, where I would think node and nothing in terms of the wave amplitude both start with the same letter, that being the letter N. Go tell your English teachers that I use the word alliteration, and I'm sure they'll be very proud of me. Okay, when does this occur though? Well, destructive interference occurs when the path difference between the two waves is half of a natural number multiple of wavelengths. I use the word natural numbers because I believe when you say a whole number, it's inclusive of 0, as where natural numbers start at 1 and just start going up by whole numbers, like 1, 2, 3, etc. In terms of this equation that describes when we could get destructive interference, we would have the path difference, PS1 minus PS2, would be equal to just some kind of half natural number multiple of the wavelength. So I suppose we could count this again, as tedious as this is. So I got PS1 to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I think this one is still 12 wavelengths. Okay, this one would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think it's like 12.5. I'm going to say 12.5 wavelengths. So that would give you a path difference that would be 0.5 wavelengths, or if you wrote it as a fraction, it would be 1 over 2 wavelengths. So again, half of a natural number, that being the first natural number of 1. So once again, why does this happen? So why is it only if you have a natural number of wavelengths do you get this interference? Well, I'm going to go back to the diagram again, and what I'm going to do is I'm going to overlap these waves, and I'm going to do that same thing where I'm going to take one of the waves, and this time I'm just going to move it over by half of a wavelength. So half of a wavelength would be the distance from the crest, a crest to a trough. So I'll go lambda over 2. And let's see what happens here. Yes, I want to keep that. Okay, so let's put the red wave on top. And what I want to do is I want to, starting at them in phase, I want to move this guy over by half a wavelength and see how these two interact. So let's move this over really slowly. Stop about right here. It's not perfect because I had to construct these waves using awkward Microsoft shapes, so they're not perfect waves, but I hope you can see for the most part that if I move that one wave over by half of a wavelength, then you would get the crest meeting the trough. Or if I went over by 1.5 wavelengths, then we would just go over to here. or 2.5 wavelengths would be located over there. So that's why we need our path difference to be half of a natural number multiple of wavelengths to get destructive interference. This illustration is of a top view perspective of something called a wave table. And the way to think about this, or in terms of how it works, is you have a couple of like these little stir sticks. We'll call this like source 1, another little stir stick, S2. What you can do is you can think of it as like these are like point sources. So if you like dropped a pebble into like S1, you'd start to produce a bunch of these spherical or circular waves that would just be directed outward. What this wave table is showing is it's showing how the different waves overlap and what the wave would what the net wave would look like as a result of like the waves passing through each other and interfering. If you look at the actual diagram, there's a couple of spots where like it seems like the wave is really, really fuzzy. So I'm thinking like right here, thinking right here, and I'm thinking about right there. It looks a little bit fuzzed out. What's happening in those spots is those are nodes. So the reason it's getting fuzzed out is because the waves are actually interfering, and they're interfering destructively to actually give you no amplitude. So no amplitude would be the equivalent of like looking at the wave table as if the water on the table was at rest. Now, halfway in between that, you get these, again, node means nothing. You get your antinodes. Antinodes means areas of maximum amplification. So if I follow like one of these green lines, so I'll do a green line here, just exactly halfway in between two adjacent nodes, we might get this. And what I can see is there's some dark spots and there's some light spots. And the dark spots on here would be a trough. And these lighter portions here, that would be a crest. So what you end up getting is something called an interference pattern. So what's happening is you're getting this alternating pattern where you have node, which is no amplification. Then you're getting an antinode, an area of maximum amplification. Then you have a node, no amplification. Then you get an area of maximum amplification, and so on. If we interpret this in terms of visible light, so what would a node look like for visible light, and what would an antinode look like for visible light? Well, a node would just be nothing. So for visible light, that would be no light. What color is no light? Well, it'd be black. And an antinode would be an area of maximum amplification. That would be spots that are really bright, if we view this in terms of light. Now let's look at what light is. We're going to look at a couple of different models of light, and then we're going to heavily expand on one of the models of light moving into the next two lessons of the unit, which again finish the unit to study off. Let's start off with the particle model. I'm going to define what a particle is. So a particle is a discrete unit of matter that has mass, momentum, and the ability to carry an electrical charge. The word I really want to emphasize in this is discrete. Discrete means that like there's some clear separation between objects. So if you had like, for example, two marbles, like one marble here and one there, these are two separate entities. So I'd say they're discrete entities. It's a bit more complicated if you have like a long string, because like you can't say the string is really, I mean, you can't say different parts of the string are like a discrete unit because it has like this significant length to it. Albeit if you compare it to another string, then you could say these are two discrete units. So I suppose discrete units means you can count the number of different units of something that you actually have. So it's a discrete unit of matter that has mass, momentum, and potentially the ability to carry electrical charge. It doesn't have to. What the particle model of light tells us is that light is a stream of tiny particles. The analogy I like to use is to think of them as little tiny bullets of light, and they radiate outwards from a source in every single direction. Immediately, this seems to be a major contradiction in terms of what we know about light. So we've said here that light is a stream of tiny particles. Well, let's go back to our definition for what a particle is. So what doesn't seem to fit the bill in terms of what exactly light is? So a particle is a discrete unit of matter that has mass. I don't think light has mass. You can't take light and put it on an electronic balance and get a digital readout in grams. Momentum? Well, momentum is mass times velocity. So light definitely has velocity because it's moving, but again, we've got this problem with the mass. It doesn't appear to have mass. And again, the electrical charge, I said it can either carry an electrical charge, but it doesn't necessarily have to. So this model immediately doesn't seem to make a whole lot of sense, because how can light have mass? But what I really want to focus on is, when we think about a particle in terms of light, let's worry about it being a discrete unit. So that's why I want to think of light as being a bunch of little tiny bullets. So for example, if we had like a wave ray, like light going in one direction to another from like a light source, think of it as like this light source firing a bunch of little tiny bullets in like every single direction. So that wave ray is actually made up of a bunch of little tiny discrete parts. We're going to get around the mass problem later, but for now, like, yes, like the light does not have a rest mass to it. There's got to be something to this, though, because this particle model is supported, or what was supported, by Isaac Newton. You know, the guy who pretty much we spent all of Physics 20 looking at his laws of, and I think he had like a major contribution in designing calculus, or at least some contributions towards calculus. So there's got to be seemingly some truth to this. What I want to consider is a small little experiment that we're going to much expand in the next lesson. Okay, so I have a light source. Now, according to the particle model of light, from this light source, we'd be firing light bullets in every direction. So you fire these bunch of little tiny light bullets, okay? Little tiny bullets of light being fired in every possible direction from the source. I'm just going to draw a few of them. To the right of the light source, we're going to view this from like a top view perspective. I have a wall, and this wall has two tiny little openings in it. Past the wall, I have a screen that I can project light onto. And what I want to do is I'm going to put this light source behind this wall, the two openings, and I want to predict what is the screen going to look like? What kind of light am I actually going to project on it? Well, let's trace the wave rays that show what direction the light would go. This wave ray, so again, from a light source, the wave rays would travel in every direction. We're just going to focus on a few of them that are actually directed towards a screen. So that wave ray would hit the wall, probably get absorbed, or some of it reflected. This one also hits the wall, gets absorbed or reflected. This one can pass through because it lines up with the slit. Oops, let's go back here for a second. If this wave ray can pass through the slit and hit that screen, then we'd get some light that would actually appear on the screen. So we get this little tiny spot of light that would pop up. Then we have another ray of light. Well, this one hits that wall again. We have another ray of light. Well, this one can pass through because it's in line at the slit, which would result in, again, you getting a little tiny bright spot. And then this one would hit the wall, either get absorbed or reflected, so we don't need to worry about it. In this tiny experiment, so where I'm shining light through these little tiny slits or these little tiny openings, if light is a particle, what I should observe is just these two bright spots, and they should be directly in line with the two openings. And that happens because only those rays of light can pass through. Only rays of light that can pass through if they're directly in line with those slits. So we get two bright spots directly in line with the two openings from the light source. All other light would get absorbed or reflected and would not make it to the screen. Now let's look at the wave model. The wave model tells me that light is a stream of continuous transverse waves radiating outwards from a source. When you think of a wave, so a transverse wave we could model by looking like this, or like typical wave shape. This is where I want to separate a wave from a particle. So once again, a particle is a bunch of individual discrete units that you can count. You can be like, here's 1, here's 2, here's 3. A wave from start to finish is continuous. It's not broken apart. So that's like one major difference between like how we view light as a wave compared to how we view light as a particle. Specifically, is a series of transverse waves. One of the other important wave properties, which I did not discuss in this lesson, but you would have read about in the self-directed assignment, is on polarization. And what polarization of light tells us is that light must be a transverse wave. This wave model is supported by Christian Huygens. And again, we've already made a reference to Huygens today by talking about Huygens' principle for diffraction. Now let's see what happened if we treated light as a wave in this scenario. Okay, so I shine a ray of light. And by the way, if you want to think of it as a wave, we're just showing what direction the light goes. I suppose you could like think of it as like light waving above this little line right here, if you wanted to. So once again, if it hits the wall, it gets absorbed or it gets reflected. Same with this guy. Now, this ray of light is going to pass through, but the thing is, waves behave differently when they go through little tiny slits. When waves go through little tiny openings or slits, diffraction occurs. But when light diffracts, it spreads out. So I have like this light spreading out as it goes from the little tiny opening or slit to the screen. Let's keep tracing the other ones. Well, this wave ray just hits the wall, gets absorbed or reflected. This one is also going to diffract. Now what we have is the light, it spreads out and now it's overlapping. So not only has diffraction occurred, but the light is now overlapping. And what's going to happen in this situation is think back to like what ended up happening on the wave table is you get this kind of a pattern. You get a pattern where you alternate between an antinode followed by a node, antinode followed by a node, and so on. So in this case, if light is a wave, continuous transverse waves coming from a source, you should get an interference pattern. This is only possible because the light spreads out and diffracts and it passes through the slits. And because it spreads out, well, then the light overlaps. And if it overlaps, we get interference. We're going to talk in the next lesson about a very, very important experiment called the double slit experiment, which has a lot of variations to it. We're going to focus on the double slit experiment with light. And then we're going to further examine this question as to, well, what is light? Is it a particle or is it a wave? For this lesson, there is no assignment. Again, we're just kind of giving an introduction here in terms of the nature of light. And then we're going to go into much more detail in the next lesson. And I will talk to you